Hi, everyone. In this meeting, I want to talk about some things that I've learned over the years about Git HTTP and how we do that in Workhorse. And the idea is to share what I can interactively before I leave the company, and it's harder to ask me questions. I've written an extended document with a big brain dump with random thoughts I could think of. And I've prepared 2 short demos. And my idea was to first do the demos, and then we can talk about whatever people want to ask about. Okay, so with that out of the way, I will start screen sharing. And okay, let's see. So the first demo I want to do is a quick rundown of what happens when a Git process clones a repository, just as a so we're on the same page what that looks like. And I enjoy demoing this with man-in-the-middle proxy. Oh, this one has data in it. Let me clear that one. So this man-in-the-middle proxy is an app that records requests. And so what I have here is a command where I use git protocol 0 to clone from this GitLab development kit instance. And this port 8080 goes into man-in-the-middle proxy, and that then proxies it to Workhorse. So now if I now do this clone, then why do I get a 500 error? That was not happening before. Okay, let's try that again. I literally did this 5 minutes ago. So what did I just break?
Obviously USB.
Yeah, or it's a problem with connecting to the beamer. I don't know what's wrong with
Aren't
this
things
guy.
always DNS?
Well, I'm using an IP address, so there is no DNS.
That's a problem right there.
Yeah. If I get an error, would it show in JSON log? Okay, that's loading. That's good. This keeps failing.
Yep, the 500 RPC code is something between Workhorse and Italy.
Yeah, I should probably look at the Workhorse log. Okay, well, different topic. Debugging. That one doesn't exist. I don't know why this stopped working. Come on. Do a clone. This is because I added some logging code and that is not creating the file. So for my demo, I added some log statements. So this thing is doing OS open file, and there is no create flag here. So it's not creating the file. So if I touch that file, then we should be good. Yes, there we go. So ignore everything up to here. So this is showing the request flow for the old Git HTTP protocol, which has a GET request that fetches a list of the references. And this is a small repository that only has one branch. And then the client comes back and makes a second request where it says, I want this commit. And these are some options that I support. And then you get the response, which contains progress messages and spec file data. And here you see the magic string pack followed by 0002 because it's spec file format 2. And there are 0003 objects in here, and that matches this. And this is a binary stream. And so this is Git internals, really what I'm talking about now. That's how things used to work. Then the Git project came up with a more efficient way to do mainly the first request with the references, because for GitLab or GitLab, this response is 10 megabytes. And if you only care about one branch, you don't want to download 10 megabytes of information about other branches. So they came up with something that they called protocol version 2. Let me clear this. And to get that, I need to remove the option that explicitly downgrades the protocol. And then what happens is you get first a GET request where the client is announcing that it speaks version 2. And the server is saying, I also speak version 2. And then the client does nothing else. And you can see there's no list of references here. And then there's a post where the client says, I'm looking at the response. It sends a command. So in protocol version 2, the client can choose different commands, and this command is list references, and it only cares about references that start with these prefixes, and that makes the response smaller. And then the server answers with that list of references, and then the client comes back a third time and says, "Okay, now I want to fetch, and I want this object." I don't know why it says that twice, but it says it wants that object twice. And then we get the pack file data again. So that was a very quick run through of what happens during a Git clone. That was the first demo. And we can talk more about this later. The other thing, unless there is a question about what I just did or anything I just showed. Okay. The other thing I wanted to demo has to do with side channels. So side channels are something we came up with to optimize the Git HTTP traffic. We being a scalability team, we worked on this, and the problem we discovered is that gRPC or gRPC Go, we're not really sure, has a throughput ceiling for how many messages you can send through it. And it was easy to, or a simple experiment showed that the machine can go much faster. So there was a problem, and it wasn't obvious how to fix gRPC. So in the end, we made something that goes around gRPC. And I can show the code for that later, but what I want to show first is just to illustrate the problem. So I made a simple example, a small example application that implements a silly RPC service, and it's based on the Hello World app of gRPC. So what it does is that it gets a request that asks for a total number of bytes to be served in a certain block size, and then that gets sent back as a stream of messages. And if you look at the implementation of this thing, this opens step 0 and it sends 0 bytes. So this is a really silly RPC, but it does real system calls, and it sends data across the line. And then I made an alternative implementation which uses HTTP to see if you can go faster. So this thing uses form values to get these numbers, and then it writes straight into the HTTP response writer. And now the funny thing is that if I go to this demo project and I build the executables, and I need to start a window with the Hello World greeter server. So that's the gRPC version. And if I then run the gRPC client, I need to pick a size. So let's say we do 5 gigabytes. 1, 2, 3, 1, 2, 3, 1, 2, 3 in 4 kilobyte blocks. Then that takes a while. So that took 8.4 seconds. And if you look at the CPU seconds, you add this up, you see 24 CPU seconds in total. So that was 300% CPU for 8 seconds. And if we do the same thing with the HTTP version, and now I need to pick a different port. That, and I run curl. And I need to set I want the same number of bytes. And I want block size equals 4096. Let's see if I got that right. That took 2.5 seconds. And if you add up these numbers, that is about 2.5. So that ran at 100% CPU for 2.5 seconds. And that one ran at, yeah, again, at 300% CPU for 8.4 seconds. And this is only measuring the client. If you go to gRPC, the server is also burning through a lot more CPU time. So this is a public repo, and I just put this together really quickly to demonstrate what the problem was. And the solution is not that we are sending the traffic through HTTP, but something else that we call side channels. But this experiment, or an experiment like this, proved that there was a problem. And that was the second demo. And in the first demo, I actually wanted to show a little bit more about the request flow on what happens on the Rails and the Gitly side, and I forgot about that. So I can go back and show that too, because that is why I added that funny logging code up here. So if we go back to this, and let's see, if I want to now truncate that file and not delete it, because otherwise I have a problem. Okay, I need to delete it and then recreate it. Or doing something like this. So this, when I do this, we see again that, why is it slow? It did the first get, it did the first post, and now it's slow. Okay, there we go. So I want to show what actually goes back from Rails to Workhorse. So that is a JSON hash with things in it like this is the Gitly server you need to connect to. This is the secret token of the Gitly server. And this is the relative path of the repository. So Workhorse doesn't know anything, and Rails tells it what to do with these JSON hashes that get sent back. And these get generated in a class called GitLab Workhorse, surprisingly. Oh, that's right here. And there is a method in there called get_HTTP_OK, which is not a good name. And it builds this hash. So that is, this is a very old code, this get_HTTP_OK thing. And I think for later features where we tell Workhorse to do something, we usually make a message specific to the thing we tell it to do. And it would, like, there's also weird repetition. Look at this GL repository. So that is in here, but it's also in the repository object. So this is a bit messy. And then if you want to see where this is used, then you can look for git HTTP OK. Oh, you don't misspell it. And then you see that there is a controller, the git HTTP controller. And this thing, okay, has a method render OK, and that is called for each of these endpoints. So it's even shared also for git push. So that's one part. And then the other part I still wanted to show here is the thing about the side channels. So we found out that if we try to push all this data through gRPC, then we hit a wall. And one crazy solution I suggested was, well, let's just establish a dedicated TCP connection and push all the data through there. But that was also complicated. And what we end up doing instead is that that Workhorse establishes a virtual connection to Gitly. And within that virtual connection, you can create new virtual sub connections. And also what happens is that Gitly makes a gRPC call, sorry, Workhorse makes a gRPC call to Gitly. And then the handler on the Gitly side establishes a virtual connection back to Workhorse. So Workhorse is then acting as the server. And then they send the data through that virtual connection. And if we want to look at that, that is in the Workhorse repo in the Gitly directory. This file. So what happens is that here we're setting up a callback for the side channel connection. So this will run when Workhorse acts as a server. And then we make a normal gRPC call. And during this line, which takes some time, Gitly makes the connection back, and then Workhorse, and then this function runs in Workhorse, and it actually copies the data around. And there's a bunch of magic in how this works, but if you want to see that, you need to look in the Gitly repository. And I won't go into it now. One thing I want to point out is that with these side channels, you must always use this close write method, because otherwise the whole thing hangs. So what happens here is that we're copying the request body, and then we're calling close write, and then we're copying the response back. And this is what I made that other file for.
Quick question. So what kind of connection are you opening to Gitly? If it's so you said it's not a TCP channel, but you make an RPC and then Gitly talks to Workhorse. How? If it's not gRPC or TCP?
Yeah. One moment. Let me just show you these logging statements I added that caused the 500 errors. Show the flow of what happens. So the Gitly call starts, and then you end up in the callback. Then the callback exits, and then the Gitly call is done. That's just what this shows. Okay. To answer your question, what's happening? Gitly has Prefect, which is a proxy that sits before Gitly. I think they're making design changes where they don't need Prefect anymore, but that's something they had to build. And Gitly and Prefect they had a problem to solve there where they wanted an inversion of control, where even though Prefect is the client and Gitly is the server, sometimes to do something related to Prefect magic, Prefect had to be the server and Gitly had to be the client. And so what happens is that we abuse a hook in the gRPC library that is meant for client-side TLS handshakes. And what we do instead is that we replace the connection object. So we also the gRPC client dials, and we also abuse a hook there so that we don't just dial, but we first dial and then we end up in this TCP handshake thing, sorry, this TLS handshake thing. Then we create a virtual connection on top of the TCP connection, or if it's encrypted, then we create a virtual connection on top of the TLS connection with a library called Yamux, which is a connection multiplexing library. Now we create a new sub connection with Yamux, and then we give that back to gRPC. So there is an abstraction layer in between that gRPC is blissfully unaware of. And the nice thing about this is that these sub-connections are connected to the right ends. So because one of the, this idea of you connect to a server and the server connects back to you, that is also something that file transfer protocol does, FTP, something we don't use a lot anymore because it's insecure. One of the problems when you do that is that you need to have a port open on the client. So the client opens an outgoing port, but it also needs to act as a server. So it also needs a server port. It needs to tell the server, this is the server port you can call me back on. And that port then needs to not be blocked by a firewall. So that gets, and if you go through a proxy, then you need to rewrite what the port is that gets connected to, because the thing, well, should it connect to the proxy or should it go around the proxy? And things get very complicated that way. And well, what we do now is also complicated, but the nice thing is that because these virtual connections are the foundation of the gRPC connection, we always know that we can get back to the right host because we stay within the underlying virtual connection. So so normally there would be a single wire going from the client to the server. And instead of that, we have a tube. We run one wire through the tube, and that's where gRPC goes. And then if we want to connect back, then we run a new wire through the tube, and we know that it ends up on the right place on the other end because the tube is already there. I've never tried this metaphor. I don't know if it's a good one. I wanted to not explain this because it's so complicated. Have I answered your question, Matthias?
I think I understand it in principle. I'm not totally sure the implementation details are clear, but that's fine. Like we don't need to get too much into the.
No, if you want to read the implementation details, you need to look in the GitLab repository, and there are packages called side channel and back channel that are both about this, and they have tests that exercise this stuff.
Got it. Thank you.
Yeah.
If I can summarize pretty quickly, the short answer is that we've shimmed in between the TLS connector and gRPC itself right here. So you only have one connection from Workhorse to Giddily. And then inside of that connection, we're actually forming those multiple channels that do the different things. One of them is for pure gRPC, and one of them is for data transfer.
Yeah. And so we use a single one for gRPC, and then each call that comes in instantiates a new dedicated channel just for the transfer for that one channel. So we create one plus many channels. And yeah, that it was a natural solution because Giddily already used this trick for something else. So we could use code that was already there. And like this whole thing where you need to abuse a client-side TLS hook to replace the connection object. People had already figured it out. So that's why it was, I think, in the end, a nice solution. Another thing that was nice is that because there is an outer gRPC call that does almost nothing, you still get logging and observability that the call even happened. Yeah, well, I think that's roughly it for what I had in mind for the demo. And then there's just 1, 2, 3, 4 pages of other stuff. Is there anything or stuff that's not on those 4 pages? Just, yeah, I'm going to shut up now and let people ask things.
What about Workhorse and uploads?
Not the topic of this meeting, but what do you want to know about it?
Like what uploads are currently handled by Workhorse? Like I know the artifacts are one of them.
By default, my multi-part uploads get intercepted by Workhorse because you can recognize them by the content type. Unless there is a rule that says, don't touch this, then Workhorse doesn't. There are also other types of uploads where the entire request body is an upload, like LFS. And there we have explicit rules on Workhorse that say, hey, you need to do something here. It's okay. Let me show you where the rules are, because that's a good question.
I think also for API posts, because they send a JSON payload where there might be some binary data somewhere in there. That's a file or something.
But that's not something Workhorse can know up front. So the way we deal with that is that we have a list of regular expressions. And on every request, Workhorse loops through these lists and sees if anything matches the request. And then for some things, it will say, I need to do something with uploading the request body here. Or, let's see, is there an example where we don't do this? There's, okay, this list is too long. There are other examples where we explicitly don't do it. Like this, this one does almost nothing. This one tries to ask Rails where it needs to be uploaded. Yeah, and it follows the same pattern. Request comes in, ask Rails what to do, and then do something. Or at the bottom of this list, there's a default route where we just proxy the traffic and don't do anything. So most requests really end up here. Well, in this one, yeah. Does that answer your question, Bob?
Yes, I wanted to see this file.
Yeah.
And Alessio's still here, so I can always ask him.
And I linked this file somewhere in the document. But yeah, this file is very important. Well, the nice thing about this file is that it's too big to fit on your screen at once, but it's one place where you can see almost everything that Workhorse does to modify traffic. We ended up with a kind of dependency injection structure, so you can also see all the dependencies come together here, and then they get, yeah, everything gets plugged together here. We could walk through this stuff and I could see if there's anything that stands out that I want to point out. The long list of stuff. Yeah, one thing I think is funny is that Git traffic, it has a mix of humans and bots. And they have different requirements. So you can tell a bot to back off, and a bot probably cares most that things are fast, and a human wants to see nice progress messages. And if you have a bot that is cloning 100 things at once and you slow most of them down, then that's fine. But if a single human who gets slowed down gets annoyed. So both these kind of traffic have to, both these kind of users have to be kept happy in this traffic. Yeah, and here I also talk about that when I joined, Git SSH was the only serious option, because if you use Git HTTP, then it would just time out or blow up, and it didn't work well. And it's funny how that turned around, and now the majority by byte volume goes through Git HTTP. Yeah, so I wrote some more about that here. Git service. Okay, that's also good to talk about. So people in infrastructure know what the Git service is, and people in development get a budget dashboard and they ask, what is this Git service thing? So this is an infrastructure thing that happened where at one point GitLab is a monolithic application. So at one point we had only one type of application server, and all the traffic went to that one type of server, and we would have n instances of that. People in infrastructure observed that when there's a big wave of fetch traffic, you get a lot of upload back processes running underneath these application processes, and they eat up all the resources on the server, and this is bad. So they said, you know what? We're going to make a separate pool of servers, and we're going to write an HA proxy rule that sends stuff that looks like Git traffic to that separate pool. And now that pool can get saturated and burn up, but normal users can still click on the web and get a page to load. So it was what do you call
This
it?
is when Git was still running on the web servers.
Yes, this was before Gitaly. So this was a capacity, it was a reserved capacity mechanism. So there was a reserved capacity for Git requests and for API and web requests. API is also very easy to write an HA proxy rule for, because it starts with /API/v4. So, and this is why I say that it's not natural to think about this if you're in development, because this split doesn't exist in the application. Like GitLab, the Rails application is oblivious to this, but this structure emerged.
Not anymore. It knows now.
It does?
But it
Okay.
still loads all 999 other controllers that will never be used.
Yes.
Yeah.
It knows
So,
now what it's running, but it's only using it for metrics right now.
yeah, okay. Because we want those metrics to make sense on GitLab.com dashboards. Yeah. So yeah, the Git service is just a regular expression, and it is defined somewhere outside the application. And I found the link somewhere. Here, there's an HA proxy cookbook that we use. And yeah, this actually also recognizes like the dumb Git protocol that we don't even support and some other things. And it also captures LFS. But these things define the Git service. So it's a thing.
It's not perfect, but it's good enough.
Yeah, it's useful that we have it now, because it is a very different kind of traffic from the other traffic that we have. And funny enough,
I mean that we also send other traffic to the Git service, but not enough to matter.
Yeah, by accident. Yeah, probably. And then nothing breaks if we do that because the application doesn't care. But if you want to think or you have to fix something about Git HTTP and you're talking to an infrastructure person and they talk about the Git service, then you need to realize it's an HA proxy regex that is invisible in the application. As a developer, it's invisible. Yeah, and it's useful for observability. I had a bit about the protocol variants. So we saw that a little bit. A long time ago, Git HTTP meant serving static files. So, you know, like the .git directory that you have for a Git repository, that's static files. And you can do some things in Git to tell it, like create some nice index files that the client understands, and then you can point Apache or Nginx at it and serve a repository. It's actually, I don't think it's dumb. They only call it dumb because they later made something that they called smart. But the problem with this static files approach is that if you only need a little part of the repository, then you're often out of luck and you have to download everything because you cannot take a big pack file with 1 gigabyte of Git data and carve the 100 megabytes you need out of it. So that problem got solved by the smart protocol, which does roughly the same thing as Git SSH. So it makes the client and server negotiate or figure out, like, these are the objects that the client actually needs. And then it sends those over the wire. And there was a version 0 of that, and there was a version 1 that failed, and then they had to skip the identifier. And then there was version 2, which I showed briefly in the demo, where they solved the problem that in version 0, the reference advertisements are too big and often useless. If you think of our CI jobs, like I said, 10 megabytes of reference data for GitLab or GitLab. It's easy to see how much it is if you do this, git ls remote. This just gets the references. I can do that. I count how many lines that is. Oh, it's even more. So it's 280 lines, and this is 22 megabytes. Okay, I've been saying 10 all this time, 22 megabytes. And a CI runner that runs a pipeline cares about only one reference, and it already knows what it is. So why force it to download 22 megabytes? And the objects, the Git objects it needs to download is about 120 megabytes. So you're adding 16% overhead to download data you don't need. So that problem got solved by protocol v2, and I think in practice it's now the dominant kind of traffic. So it's about the request flow. Let's see, authentication. Yeah, that's a funny one. Git prefers to be anonymous, the Git client. So it's even if it knows the password it needs to use for a private repository, it will always try to clone it without sending the password. And then the application returns a 401 unauthorized response, and then Git tries again with the password. So that means that the Git service serves a crazy amount of 401 responses, and it's normal. One funny problem that this creates is that at one point we created rate limiting to detect brute force password attacks. And we had to be very careful because it looks like these Git repositories constantly get brute force password attacks because of all the 401 requests. So there's code in there that sees, oh, this IP came back and now it got the password right. So we reset the counter because the 401 was expected. That is a weird property of Git HTTP traffic.
That's actually very similar on how the Docker registry works, container registry. Is it almost all of the clients assume that they don't necessarily need authentication until they actually connect for the first time and they get that initial, oh, but I need your auth realm response. And then once they've done that, they'll know, oh, okay, next time I should continue to use this authentication I did last time. Git is just, it's got more of a goldfish memory. So it tried, oh, I need to auth. It tried, oh, I need to auth. So
it's it remembers. I think this is a feature of libcurl, and Git uses libcurl, and I think libcurl remembers for the length of the process, or it has some sort of client object, and for the life of the libcurl client object, it remembers that it needs to send the credentials. And it does 2 or 3 requests. So the second and the third request don't do include the username and password. But after that, yeah, the goldfish has forgotten, and it needs to try again.
Right.
It is nice that it uses libcurl, because we have support for Kerberos authentication, and that works on the client. Git probably has very little. Oh, now I need to think hard. No, actually, I think the Kerberos authentication is a can of worms in Git, because with Kerberos you get a way weirder cycle with retrying 3 times before you have the right ticket. But that's a client-side problem, not a server-side problem. Buffering, also an important thing. That's one of the things that serving Git HTTP from Rails did wrong, is that kind of the natural way to serve a response from Rack in Ruby is to just say, here's a string that is the response. Here you go. You don't want to do that with 1 gigabyte of data if you don't have to. So buffering is a problem, and everything along the way that might buffer needs to be told not to buffer. So we have explicit configuration in Omnibus that tells Nginx to not buffer the requests that go to Git endpoints, not buffer the request. And on the way out, Workhorse sets a special header that Nginx understands, called XXL buffering, to say no, don't do this, because otherwise, if you're doing a 1 gigabyte clone, Nginx would end up creating a temporary file of 1 gigabyte, and the user sits there waiting until the entire 1 gigabyte file has been written to disk on the server by Nginx before any bytes start going to the user. And this is bad for Git HTTP, because you know this progress meter where it says, what does it say? I always forget. Let me just do a clone here, then we get the progress meter. Come on, don't be slow. Oh, we don't see the progress. We don't see the server side progress meter because it gets hidden by buffering. But this one, receiving objects, this is a process that runs on my laptop called git index back, and it's only received 70 megabytes by now, but it's already doing work that has to happen. So because we're not buffering the response, this client-side work can start immediately. If Nginx would have buffered the entire thing and then started sending it, then I would still have to do all this work afterwards. So it's really important that we have an unbuffered channel so that this work can start happening as soon as possible. This work. And the same thing happens when you do a git push. Then Git also runs git index back, but it does it on the server. So you want the moment you start pushing data, you want to get that index back running as fast as possible, so that the end-to-end time to handle the pull or the push is as short as possible. So buffering bad, and we actively make sure that buffering doesn't happen. For small requests, buffering is great, but yeah, for this stuff, it's bad. And you don't have to worry about this probably because we got it right. Also, I don't know how if we even, Jason, did we have to do something about this for Cloud Native?
Yeah,
Is there
it's
anything
been
that would
fun
buffer?
to tweak. Because it really comes down to a lot of implementations. When we're dealing with static infrastructure and an Nginx or an HA proxy config, you can actually turn buffering on per request path.
Yeah.
Or per backend that you're going to. That's not necessarily true in all cloud providers. So whether it's, Cloud Native and the Helm chart that we have that includes the Nginx ingress controller, or you're in AWS and you're making use of one of their load balancers or their application load balancers, or GCE and their own version of an ingress controller and whatever is backing that. It gets fun trying to explain to people, but we want to have buffering on because the images load faster. So I understand, but if you turn this on and you set it too high, all of your CI load's going to take forever and it's going to hurt. So which
Yeah.
way do we go? Because sometimes we can set it on a per path.
Yeah.
And a lot of times we basically have to go, it's either on or it's off. Sorry.
Yeah. So something I've wondered at times is whether Workhorse should do the buffering for small requests, because then you can turn it off everywhere from there on. But this never seemed important enough to work on, and it also, I mean, getting a cache like that right means you need to be very careful about memory management and not running out of memory. And I thought, well, Nginx knows how to do this. Let's not do this. But if I hear you talk about these ingress controllers, maybe one day it would be good to do this in Workhorse. Don't know.
So, honestly, at a certain scale, when it becomes a problem, it really comes down to, should we do this in the application? Because for anybody who's listening, there's a word Jacob said
We're all
multiple
listening, Jason.
times. Memory. There's a big fat difference between I have it running on a VM and I have the whole VM's worth of memory and the kernel can fight it out. And highly constrained and controlled environments through namespaces, which is how they're implemented as a part of Kubernetes. If you say, I don't think I'll ever need more than 2 gigs, well, it's going to hold you to that. And the moment you cross that line, it's going to come down with an axe, not a, hey, can you stop? It's going to just, you're gone. Sorry. And if you are doing buffering inside of a process like this, you have to be extremely careful of how much is actual in-flight data and how much is buffering in the requests, and optimizing to never approach those limits too closely, because maybe a new connection comes in and all of a sudden you've got an extra 5 megs for just a split second.
Yeah.
You're
No,
gone.
getting this right is hard. And to answer what I was saying before, if we really need to add this kind of buffering, it would probably be better to have an Nginx running somewhere and tell people turn off buffering on your cloud ingress, and then we put an Nginx with the correct rules that either does it or does not buffer, than trying to make a proper buffering proxy in Workhorse.
Yes, let us not reinvent the wheels. I'm very happy
Yeah.
to put a small person with a flag in front of things rather than reinventing all of the wheels on the car at the same time.
Yeah. And there's a final thing I put here, which is about the request before response buffering. And I feel really bad about this, but I don't remember why we added this, and it's really complicated. But I don't know if it's safe to remove it. So the problem is that HTTP 1.1 has a strict request response cycle, and it goes typically through a TCP socket, and a TCP socket doesn't care if you start writing the response before you've consumed the request. But I think some proxies might care. So we have some sort of extra safety thing in Workhorse that stops the response from going out before the request has been consumed. And it's in this file, and it creates a temporary file if something starts writing too soon. And I don't know, it's just too many lines of code. Like, I mean, look at this. This is 100 lines of code to do something that I'm not even sure is necessary. If we want to get rid of this, we should see if it ever creates a temp file in production. If it doesn't, then apparently this does nothing. But yeah, I'm not going to fix this in the time I have left. But it's there because at one point, I think it's there because we got complaints about weird errors. And if we did this, we could say, well, we can make the error go away, but maybe they get an error at another point or somewhere down the line. Oh wait, I shouldn't stop my screen share because we don't know if we're done, and I end up constantly talking about other things. I should go to the document.
This particular problem isn't like magically isolated to Go. It happens. I remember running into this way back in like PHP 3 days. It's a little funny when you started responding before the full body
Yeah.
came in, and either the runtimes would get weird or the upstream that was actually in front of your CGI would just go like, wait, what? So it's that particular challenge is not new
Yeah.
to the space.
And the reason we have this problem is that we are essentially doing CGI, and the timing of when the response starts coming is out of our hands because Gitly does that. And Gitly runs a Git upload back process, so it really depends on what that process does. Now, I think that on the happy path, it always does the right thing. So I can only imagine this being a problem if upload back bails out and wants to say no, or this is bad. But that's why I'm not entirely sure we need it, because I think upload back just does the right thing. But it's there. And it has to do with Git HTTP, so I put it in this document.
I mean, that's a good thing for people to know. Like, trying to describe how the evolution of the request flows have actually worked for Git HTTP has been complicated at times, because I've been here through some of these evolutions, and like, how does it work? Where does it go? Why does it go? Where does the storage work? And actually walking through how those function in the past versus how they work now versus how so many components will actually just shortcut and go directly to the thing they need to talk to now. Whereas in the past, it was request in, okay, over here and back, over here and back, over here and back. We'll just watch this bouncing request happen. Now we're a little more smart about it, but these are not simple requests because of the nature of the information, the authentications, the authorizations that have to go around, and the verifications of those checks too.
Yeah.
We can't just blithely trust that the person said, when I say the person said that the service that made the request on behalf of the user was accurate, but we have to prove at the same time for audit purposes.
This of course started out simpler. So there was an open source rec middleware that would spawn an upload back process from Ruby and send the response back. And we used the Rails router to mount that somewhere for the things that ended in .git. And then at one point we forked that to integrate it with GitLab authorization checks. The thing was called grec because Git and rec. So there was GitLab grec. And that was the thing we were using when I joined. But that had the problem that it was in the Ruby process, and just the timeouts make it a bad idea, because people should be able to clone a large repository without running into a Ruby request timeout. And because Ruby application threads are a scarce resource, you need timeouts to not let them all get eaten up. So that didn't work well, and yeah, so the moment we introduced Workhorse, we ended up with this authentication dance where Workhorse needs to ask, is this allowed before it can run the Git upload back process? But that would then sit underneath Workhorse, and Workhorse would have access to the repository via NFS. And then we introduced Gitly, and we said, okay, you cannot get to the repository anymore via NFS. And so instead of Workhorse spawning that upload back process, it needs to make a Gitly call to Gitly, and then Gitly spawns the upload back process. And if you're on an omnibus box, this all happens on the same box anyway. And it looks complicated, but it's there so that on github.com we can pull these things apart. It's also okay to ask other Workhorse questions or make comments. I don't know, we're all here. I really like Git HTTP, but not everybody has to be as excited about it as me.
To be fair, it's a core piece of the functionality, so we all need to be at least a little interested.
Well, I've walked through this document, and there are no extra questions. Okay, there was some stuff added by Sean, I think. WebSockets. Yeah, WebSockets are we have two things with WebSockets. We have a wacky feature that connects to a Kubernetes container and gives you a shell in that container, so you can type into your CI runner container. And that's called Web Terminal or something. And I've never used it myself, but that thing uses WebSockets both to talk to the I think it uses a WebSocket to talk to the container, and it definitely uses a WebSocket to talk to the JavaScript front end. And Workhorse sits in the middle and copies messages back and forth. And that is called channel, because that makes a lot of sense. So there's a proxy function that calls read message and write message on a thing. And I believe there's actually something in here that rewrites terminal codes because otherwise the JavaScript client crashes or something. There's some funny application specific stuff going on here, but it's been a long time since I looked at it. So that's one. The other, interactive web terminals. Thank you, whoever put that there. The other thing is Action Cable, which came later. And for Action Cable, we don't have any kind of, so interactive web terminals actually make a new connection to that container. So they need to do something special because the point is talking to the container and not talking to Rails. Action Cable, the point is to talk to Rails. So we don't really need to do something special. And that is handled in the router. Well, it's handled by the Go reverse proxy library. So almost all the code goes through this. Sorry, I misclicked. This proxy thing, which uses this HTTP util use single host reverse proxy from nets HTTP util. Yeah, so we're really glad that this is a very solid reverse proxy because all our traffic goes through it. And this thing supports what is it called? There's is it upgrade or connect? There are some hijacking mechanisms in HTTP where you can say this HTTP connection. Sorry?
It's upgrade, yeah.
Upgrade, yeah. So it supports upgrade and WebSocket uses upgrade. So when the client tries to make a WebSocket connection, at some point it says upgrade, and then this reverse proxy says, oh, okay, you go do, I'm just going to copy the bytes route now and not parse requests anymore. So that's why that works. And the other thing we had to make sure is that some of our, I'm not super sure why, but there's all this processing logic we have and we bypass it, I think, on cable. Let's see, cable proxy. What is cable proxy? Yeah, there's a lot of extra stuff here that is not going on in cable proxy. But that's all Workhorse really needs to know to proxy Action Cable, because the hard part is done by the Go standard library. GitLab runner interactions. That is
before we move
yeah.
on, given there is a lot of people here, it's worth mentioning that the first thing, the interactive web terminals, is based on Gorilla Mux library, which has been archived a couple of months ago. So we are actually running on an unmaintained library. So there's maybe something
there's
to be
an
aware
issue.
of.
We need to replace that library with something else. Luckily, that directory, like where it gets used, it says this channel directory. It's a couple of files, so it should be doable to replace that. But yeah, thank you, Alessio.
Is there a recommended other library we can use? No, too easy.
There's an issue about this, but I don't remember where it is, and because we're recording this, I don't want to pull up an issue list that has confidential issues in it.
Yep.
Is it a popular feature? Do we know how many users actually use that?
I think it's disabled on GitLab.com.
But is it enabled by default?
I don't know. It was reading the documentation and say that it's not enabled on. So shared runners on .com does not provide interactive web terminal, and there is an issue to follow for those things. So maybe if you are bringing your own runners,
you can use it. Yeah. I wonder if you're suggesting, Matthias, that we kick the feature out. That would be nice.
It's always the first thing I suggest. I think we suffer sometimes from feature-itis a little, and like things that were added 6 years ago that sometimes they come through community contributions because like one person needed them. And then it's, we always then need to maintain these things in perpetuity. And I think that adds a lot of strain.
Yeah, there's also the thing that is integrated in the web IDE. So one of the feature was that you code and you have a shell when you can test those things as you like.
Yeah, that was my understanding, that it was for web IDE type functionality. Oh, somebody found the issue. Thank you. And if we look in that issue, then I think there is discussion of alternatives or not.
I think you're mostly talking with yourself there.
Yeah, well, but probably something else might. The problem has probably been solved by other people for other Go apps in GitLab. So we can look there which libraries they picked.
Sorry.
No one seems to have solved it. Everyone recorded that there is a problem, and there's no discussion in any of those issues.
There's some basic functionality in standard library, like in Go language, but even the standard library documentation mentions some third-party library and says that there are more like rich features in that third-party libraries. So please consider using that library.
It depends. If we can get away using the standard library, then we've
maybe it's better,
one dependency less.
Yeah.
But yeah, it's one of these technical dev things that sits there. Yeah, GitLab runner interactions. That is also some interesting code. GitLab runners are constantly polling GitLab.com, and they do it so often, and there's so many of them that it's too much traffic. So we have a feature where the Workhorse reads the response, and if it doesn't look good, or if it looks like the runner already knows this, I think there's like a token that says what the last state is that the runner saw, like an opaque token. And if that hasn't changed, then Workhorse just doesn't respond to the runner, and it sits there and it thinks it's doing a very slow request. And Workhorse then listens on a Redis channel to see if on a pub/sub channel to see if anything changes for that particular token. And if it changes, then it wakes up, it writes a response to the runner, and the runner gets to work. So it gives you a nice quick response without, it's long polling, and it gives you a nice quick response without needing frequent polling. And it's another inversion of control principle, just like with the reverse Gitly connections, really. It's the funny thing, it has a problem in that it's disabled and self-managed because, well, we meant to enable it, but we set the default time to 50 nanoseconds and not to 50 seconds. So it's effectively disabled because 50 without a unit is nanoseconds. And we can't enable it for runners because the way the runner code fetches jobs and the way the API endpoint is designed, you cannot rely. If a runner has multiple tokens, say 5 tokens, then what it will do is that it requests each of them in turn in a loop. So if there's a job for one of these tokens, it gets it reasonably fast because its turn comes up. But if the concurrency setting is low on the runner, and we make these slow requests, then it spends a minute waiting for one, or 50 seconds waiting for one token. And if a job comes in on the other token, it doesn't get picked up for 50 seconds. So this way of requesting one token at a time is problematic. And then you could say, well, why doesn't the client just fire off 5 requests at the same time? The problem is that if the server responds with the token, then the client has taken on the obligation to run the job. So if the client has concurrency 1 and it's asked for jobs on 5 different tokens, then the server can, worst case, give 5 jobs to a runner with concurrency 1. And then the job also takes a long time to run. So the design of the API endpoint for fetching jobs does not deal with having multiple tokens and concurrency well. Like, I'm almost reminded of how we deal with psychic queues and weird BR pop stuff, but it's problematic. And we don't have the problem on GitLab.com because we always use runners that have just 1 token. So they can, because they're shared runners and they are runner managers, I think. So they probably, the runner manager is polling and then it can fan out the work. So it's okay that the requests are slow. I don't know if this is easy to follow without code, but I talked about GitLab runner interactions there. Well, we've been here for an hour, so I think it's okay to wrap up. Thank you very much for your time and questions and participating. And if anything comes up because of this, or if you are watching a recording and you're thinking, hey, what's going on there? Just ping me on Slack, ask me if I'm still there. If not, or no, wait, go to the Workhorse channel and mention me and ask there, because if I'm still there, I can answer you. And if I'm not there, somebody else can answer. But what I'm trying to say is that I'm happy to share more if anybody who wasn't here has questions.
Thank you very much, Jacob.
Thank you.
Will you do the honors of stopping the recording, Jason?